So yeah, welcome to mini tutorial 3B. Thanks for coming. I tried to fit as many buzzwords into the title as possible. I'm sure I could have fit maybe 2 or 3 more, but I think 3 was enough to get you guys here. So that's good. Doug already introduced me. My name is Rashawn. I'm a computer scientist that works for engineering groups, specializing in statistical modeling and the like. Here's a little bit about what this mini tutorial is about. I have like an ambitious amount of content to go over, so it'll be like a very brisk pace, but overall, the goal is to discuss artificial neural networks and the topic of deep learning at a very layman's terms level. I'll try to make it as conversational as possible. I'm sure listening to all the talks that have been going on, it may be elementary for a lot of you, so I apologize for that in advance. But the beginning half of the tutorial will discuss the theory behind artificial neural networks, and then in the latter half, we'll talk about how to implement some of these using Google's TensorFlow API for specifically Python. The API is available for a lot of other languages, but I'll go over Python for now. And even the implementation details that I'll go over will be a little bit, I want to call them a teaser. TensorFlow's API is very rich. You can do so much with it. And all I'm doing is walking through how to make 2 different types of models. Talking through a little bit about how this is going to work. I have a tablet, and on the side here, hopefully you guys can see it in a separate window, I'll be doodling just to walk through some of the lecture material. I find that it's easier to like discuss things this way. If I have a write too small, or one of the colors I use is like too irritating for you, please just let me know. I have a ton of colors to choose from, and I'll switch between them pretty often. At the same time, Victoria is assisting with this mini tutorial as well. She'll be moderating through the chat. So if anybody has any questions, please throw it out immediately. I have a game plan about all the stuff I want to go over, but I would much more prefer this to be as organic as possible. So if any questions come up, I've asked Victoria to interrupt me with answers, or maybe just like spark a discussion on the spot, because I prefer it to be during that phase of the lecture rather than at the end and then like maybe going back, because I'm sure other people have the same questions as well. Alrighty, so here's a rough agenda of what we're going to do. It's broken down into roughly 3 modules, and then there'll be a little 5-minute break at the end, but mostly that break will just be pausing for questions, I think. All right, so starting off with the first module is background and context. I like to talk about, every time I discuss machine learning, deep learning, or any kind of artificial intelligence topic, I always preface it with like a couple of slides that are similar to this, where I talk about what AI means, what machine learning means, what data science means, because lately these terms are so overused that they ultimately mean nothing, you know? So before we start to talk about like maybe more dense technical topics, I'd like to like lay down the groundwork of what I believe, what I'm going to refer to when I say AI. So in the context of a Venn diagram, AI is one bubble, and I would define it as computer programs that ingest stimulus, deliberate, and make decisions. Very broad, and it's purposely broad because so many things are encompassed under the AI umbrella. A subset of AI, I would define machine learning. I would define as machine learning, and we'll talk more about the details of this, but for now, I'm just going to say that they are data-driven models. And then eventually what we're going to get to at the latter half of this lecture is talking about deep learning, which I'll abbreviate as DL. And just deep learning, as a teaser for now, is basically just neural network modeling. Anything related to neural networks is a synonym for deep learning. Another buzzword that's often used that is kind of like its definition has been molded. It's kind of a bubble that intersects all the ones that we've drawn so far. It's data science, abbreviated as DS. we'll define this as statistical. Statistical sciences with applied AI. Another good way to I choose to think about all this that I borrow from other lectures that I've had is an output of an AI project is usually some sort of software, right? The software program that is Siri or Alexa, whereas the output of a data science project is usually some sort of report or maybe a recommendation, even getting more realistic, a PowerPoint. Yep. PTX, right? So data science is more so like the applied use of artificial intelligence, machine learning, and deep learning implementation for the use of actually coming up with a decision or recommendation of something. Whereas the goal of AI is entirely the computer science aspect of it to produce a software that does a thing, whether it's like interacting with a larger environment or just predictive modeling. Again, feel free to interrupt whenever you guys have questions. So here's just a summary on the slides of what I just talked about. I also want to talk a little bit more about what I mean by AI, and I'll talk about this one particular subset of AI called the symbolic agent or symbolic agent architecture. In the roughest terms, it can be defined as an agent taking action to influence its environments and the environment responding back, changing in some sort of way, and then giving percepts back to the agent so that it can update its own knowledge base about how the environment works. I like to think of it literally as like a little robot with a brain, and that little brain has like a semantic conceptual understanding or a semantic logical understanding of how its environment works, such that when it takes actions, those actions are logically based and well-defined. And when percepts are given back to that agent, it can update its own mental knowledge base, or I shouldn't say mental, but its own logical knowledge base of how it interprets its environment to make a decision. And none of this necessarily has to be so mathematically defined. It only needs to be logically defined. So entirely it uses a symbolic representation, which is like a more so on the side of discrete math. And the goal of producing agents in this way, and the goal of like agent-based architectures and building symbolic agents, or I want to call them logical agents. Their goal is really to encode rules, encode rules and domain knowledge directly into like some sort of knowledge base that the agent carries. Sometimes people like to call these expert systems. The term expert system has become a little bit more derogatory lately as deep learning has rose. I think that's a little bit pompous, but expert systems definitely have their own place. They're very useful. And if anything, I feel like the rise of reinforcement learning is like bringing them back into the forefront, using like ontologies and epistemologies to define an agent, and then deep learning and machine learning when necessary for those decision policies. Right, and the term expert really comes from these agents being able to, or like perform as experts in a specific scenario, where they're not well-versed or designed so loosely as to generalize to other kinds of situations as well. Right, so here in the PowerPoint slides, I have a couple of examples of what expert systems might look like. Here's one of our Mars rovers. Basic example of an agent interacting with its environment and then gathering percepts about its environment to make some sort of decision. An example of a problem that this agent might face is maybe finding soil deposits to collect for analysis, right? Every soil deposit it needs to mine for is a very specific, like there's a lot of cost to it, right? It takes energy, time, and all of that to do it. So you want to selectively and intelligently choose soil deposits to analyze. So the agent is, the rover is equipped with a bunch of different sensors to be able to gather percepts from its environment, to deliberate over something, and then ultimately take action on this environment. Overall, that software program I would define as a logical symbolic agent. It'd be a good solution to the problem. Emphasis on what logical agents like to leverage is efficient search strategies, expert domain knowledge, and formal logic. And again, I want to emphasize the formal logic part, which is directly a result of having their knowledge base be semantically relevant and like rigorously defined. A lot of epistemology and ontology goes into defining what the knowledge base agent perceives, and then formal logic can be applied to make basic decisions about it. So that again boils down to just hardcore discrete mathematics. Here's a fun example from OpenAI that I really like. It's a bunch of little agents running around and playing hide and seek with each other. This is an example of a reinforcement learning problem over like very rigorous sets of training, but it again boils down to a symbolic agent architecture and just agent-based architecture, which each one of these guys has different goals and different ways to interpret the environment, categorize those things into its own mental knowledge base about what the scene is like, mix that in with its own goals and maybe costs to be able to deliberate and make a decision. And then there's a cycle of percepts, agents, percepts, and actions. So now consider cats. I love this part. Right, so where can agent-based architectures kind of go wrong or fall flat? A perfect example is the most important problem on the internet, being able to classify images of cats as cats and maybe images of not cats, such as this fire truck over here, as not containing a cat, and completely uninteresting image. Being more technically rigorous about what I mean by building a classifier to detect cats is this statement over here. This configuration of pixel values, because ultimately images are just RGB values, or if it's grayscale, just individual values per like this grid, right? They're just floating point numbers, pixel values that like when arranged in some sort of way, we as humans can interpret it as an image. So this configuration of pixel values, does it have a cat, right? I'm trying to like dissociate some of the human concept of cat from what this image is, because computer programs don't understand ultimately what cats are. So if we were to build an AI agent for it, we would have to logically define what a cat is. And more than that, we would have to logically define what a cat looks like when it appears in an image, right? It has two eyes, whiskers. What color are those eyes? Well, let's look at our reference images. It seems like they can range, so I'll go back and include all the different color types. Going back to the image, it looks like some of the cats have obstructed views of their eyes, so maybe like not always two. And then it looks like cats can sometimes wear hats, so hat, maybe. And then I can go on forever with like trying to define logical rules that like fit into a semantic database for helping a machine understand what a cat is, right? And I'm still at the concept level, or like maybe like the superficial perception level. Going even lower than that, I still need to define how to understand the pixels, like this a general region of the image, and interpret it as like a cat's ear or maybe a cat's eye. If you can probably tell where I'm leading down with this, but this is too difficult. The problem of modeling what a cat can appear like in a group of pixel values is too complex of a problem to model, because there's so many rules that you have to encode and so many exceptions to those rules that it ultimately becomes meaningless. And that's where machine learning really can come in as like a more optimal way to solve this problem, solve the problem of classifying cats. Instead of logically defining a cat, what we can do instead in this brand new internet age of databases and large data is have a rough meta model, right? Like a mathematical meta model that accepts some sort of loose parameters for something, so, such as parameters for pixel values across this image. and feed it a ton of examples of cats on the order of 1 million, because we have lots of pictures of cats available. And at the same time, we'll give the counter example as well, which is pictures of images with no cats in it, right? The negative sample, the negative class. And what we will hope that this new model will do is glean aspects of these pixel values, patterns between specifically these pixel values that are in common within the set of images that do contain a cat. And then the same thing with the negative class, the set of images that don't contain a cat. And through the process of training on these images and learning parameters that differentiate between these and ingesting large amounts of data, machine learning is able to solve this problem, and like surprisingly well. In fact, like insultingly well, how well it does it. So just summarizing what I described there, and again, all of this is just to provide context too, so that we know exactly where we are, so we can talk about deep learning in a few minutes. All right, so AI specifically logical agents are logically defined, usually have agent-based architectures, right? Which is that whole, like, I have a system that interacts with the rest of its environment, and I want to track those interfaces and understand the percepts within a semantic model, that whole thing. And oftentimes, complicated searches are involved, which is the case for like most of the popular programs that were able to beat humans in things like chess or Go, usually leverage like pretty sophisticated search techniques. On the other end, what we just talked about was machine learning, which is entirely data driven. There is some sort of prerequisite model that we have before we have all of our data be ingested by that model, but it's nowhere near the rigor that we would need for AI overall. AI is rough, like you develop an epistemology or ontology of what a cat looks like in an image before you even start. For machine learning, you just have a rough mathematical outline of how to ingest image data, which is, again, ridiculously easy. And then a byproduct of all of this training is that you assume all the characteristics of what a cat looks like, or how a cat can appear in an image from the data itself. So it's like you're assuming a model, a meta model over how nature works through the data itself. Again, starkly different from how AI decided to handle it. On an AI project, we would apply that meta model up front and then have the agent be let loose into the environment to learn and stuff. Machine learning is the opposite, at least the more traditional sense of machine learning. Obviously, these fields have been a little bit blended lately as reinforcement learning starts to become more popular. So here's a summary of what I just said. A lot of text, but most importantly is the thing in the little banner over here. Rather than logically modeling nature, machine learning, and then again, deep learning, remember a subset of machine learning, assumes a model using the data. This whole ontology thing is not really so much required when you build a machine learning project. Of course, it's very useful, right? It's useful for the process of feature engineering, domain research and all of that. But in terms of just discussing like these broad techniques, machine learning will assume a model of that closed case study using the data. And of course, I'm sure you guys are familiar with the two types of machine learning: supervised learning, where it's predictive modeling. You're trying to predict an output based off of a set of inputs. An example of one is shown on the right, which is a classification problem. I have a bunch of data points spread across point space, and I have a decision boundary here shown as a dotted line, separating my data into two classes, this blue class and this red class. That's an example of a classification problem, which again is a subset of supervised learning, predictive modeling. The other type that we're not going to talk about so much is unsupervised learning. I just included it here for completeness, and that is really very ambiguous. Understanding the essence of your data, understanding the patterns that exist in your data, or maybe describing it in more simple ways or more complex ways, just learning about your data in general to like I guess, just glean more insight from it. And an example of that is over here with the clustering, right? I have that maybe a different set of data points, and I want to identify two different groups of data. Maybe they were collected in different regions or something, and my data should be able to show that there's clearly two distinct categories of things. That would be an example of supervised learning. We're going to be talking about deep learning, which is entirely which is on its own a predictive modeling, a predictive model. So all neural network models are built for the purpose of predicting something. That being said, you can use neural network models for supervised learning techniques if you just use it as like a cog as part of a bigger machine. All right. This is another example of one of those things where I'll ask a lot of you guys to be a little bit more patient because it's a little bit more rudimentary, I guess. But I think it's important to describe what learning is so that we can talk about machine learning a little bit better. So for machine learning specifically, learning, this is a very complicated idea philosophically. For machine learning, it's not so much. It's an iterative method for optimizing a set of parameters over like a template model based off of a data set that you have. So over here, I have a data set of a bunch of points. They appear to be trending linearly. And what I'm going to do is guess what a good model fit would be. In fact, I'm going to, let me be a bit more descriptive about it. I want that model to be of this form, y equals mx, and my only parameter is m, the slope of the line. So it has to pass through the origin, and I'm going to guess a random line to start off with. This random line is pretty bad at being a predictive model, and specifically, I can measure how bad it is. Right? If I take a point and I compare it with what I thought the point should be, I have a residual or an error term, and what I can do is what I can do is like define a specific function to summarize how wrong this model is, right? I can go through each one of the points, figure out what the length of all of these lines are. It's customary to square them so that if one of the points was underneath it, it would cancel out. Another rationale for squaring it is that you want things that are more wrong to be even more emphasized as wrong in your error term. But anyway, what I have is a value, a numerical value that measures specifically how terrible this teal line is, how terrible this teal line is at explaining my data. So as my next step, maybe what I'll do is guess somewhere else. Guess somewhere else like that. I will be able to know what direction to go in until I have a model that is of good fit. And what does good fit mean? It performs well on this training data set. And what does performs well mean? Well, I've decided a metric to use to gauge if this model is a good fit for this case study. And overall, that's what learning is, right? It's this guess and check kind of iterative process of fitting a template model, which in this case was just a linear model, to a large data set where we define how well it performed, where we get to define how well it performs, right? Like I'm arbitrarily telling this model, look at this parameter and optimize over it. So I like to mention this because learning is an overloaded term, but ultimately it has a very simple definition and like a kind of dumb, like plain flat definition when it comes to machine learning. And again, I can be very, very, how do I say, algorithmic about this, right? If I decide to maybe plot each one of my guesses on a plot of error versus my parameter value, the slope value, you'll see that I'll slowly get this parabola shape. This lends itself to a lot of good optimization techniques, which is like one of the driving points, one of like the driving algorithms for learning in general. And the most common is gradient descent. Right. The idea of gradient descent is that at each one of these points, I will figure out where it exists on my error versus parameter plot over here. And I'll be able to take a differential on that point to know which direction I need to go in, which direction should I adjust the slope in to perform better on my next iteration. So I will kind of descend over this this error function over here until I'm at a value within this little trench over here that I would consider A-OK learning. So this is an example where all of the points intersected over the origin. I can very easily decide to add more points to it. I can very easily decide to add more parameters to it. For example, maybe I didn't want it to be tied to the origin over here, and I want it to be a free-flowing line that can exist anywhere on the 2D space. Now my model function changes to y equals mx plus b, right? Where b is the y-intercept. I can also write that as just replacing all the variables with a w subscript. And all of a sudden, the only thing that changes is my error plot, the same one that I drew up here, is now 3-dimensional. And this concept arbitrarily stays the same no matter how many parameters I have. And gradient descent remains the same. Very powerful technique. All right, so here's just an animation that summarizes what I was saying, and a simple 4-step process that kind of for dummies what gradient descent is. Learning is improving performance on a data set, right? So deep learning and all of that, the learning part just means performing well to a data set that you give it according to a performance metric that, again, you give it. Right? It's not learning human concepts or anything, not necessarily, unless you've cleverly crafted your performance metric to reflect that. There's more of the same thing, more details about gradient descent that I'll breeze over. And again, if I choose to add more parameters, this red line you'll see is not affixed to the origin anymore. It is scaling wherever it wants along the 2D plane, along the 2D plane here. And that just means that in addition to m as a parameter, the slope, I also have b, the y-intercept, as a parameter. But you'll see that gradient descent remains the same. All right, it's the end of module 1. Just again, laying down like a good foundation so I can talk about words.
Hey, Rashawn, can you hear me?
Yeah.
Cool. So we just got a question that says, can we think of machine learning as just statistical regression modeling, or is there a distinct difference between the two?
So when I'm using the word machine learning, I'm talking about it as all of supervised and unsupervised learning. So I would say it's a little bit more than just regression modeling, including classification and all of the techniques for unsupervised learning, like clustering and all of that. Hope that answers your question, Rebecca. Yeah, with these definitions, I'm being super duper broad. And really, I'm just trying to scale down, like starting from very loud cloud of buzzwords, and then hopefully focusing down to something so we can talk about what deep learning is. Any more questions?
That's all for right now.
That sounds good. All right, so module 1, 0 indexed, the best index. Deep learning terminology. I mentioned this before. Deep learning means exactly the same thing as just anything with neural networks in it, with artificial neural networks in it. If it contains a neural network, you can say that you're doing deep learning. And neural networks are also not, I'm hoping to disambiguate what neural networks are to the point where you see them no differently than a regression model or a basic logistic regression model for classification. It really is just math, and then it just has the ability to become very complicated very quickly. But that doesn't mean that it's too complicated to understand, right? It's just very good at modeling complex phenomena and looking very confusing, but really just find solace in the fact that it's really just math, not magic. And this is typically how you might see a neural network diagram drawn. A couple of inputs on the left and an output on the right, with a bunch of lines and circles and nodes and stuff going in. This is a good representation of how neural networks work. Really, it's just a pictorial representation of what how the math looks going into it. So let's talk about how to like build up to what one of these circles means, what one of these nodes means, with an example of predicting housing price. Housing price by using the size of the home, the square footage. And Needless to say, I made this data up, but you can see that there's going to be some sort of, the optimal model maybe has like some sort of trend like that, and then tapers off, right, to 0 for any value below some sort of threshold, right? So what we can do is, let me start to draw what a neural network model might look like. As an input, we'll have size going in, the numeric value into my node. And then as an output, I'm going to have housing price. Housing $sign. In the more traditional form of neural network design and neural network like compute nodes, each node can be broken down into 2 steps. 1, 2. So for step 1, we have a linear combination of all the input parameters, right? So in this case, it's pretty simple because we only have 1 input parameter. It would be y. It's called y prime. Y equals mx plus b, where x is the size going in, right? There's also a bias factor. We'll call it W0. So let me rewrite this. Right. And essentially what I'm doing here is just performing a basic linear combination over the inputs. If I had another input over here, I'll just call it x2 going in. My first step here would change to plus W2 times x2, whatever that parameter is. Just a very, very simple linear combination of all the things going into the node. The second step is a activation function. Usually people use g of x to summarize this. And what you'll do is just simply apply that activation function over the output of the thing from step 1. An activation function really can be anything, any kind of change or adjustment you want to make to the output of the parameter from before. Customarily, you'll do something like a sigmoid function, right? Just the exact same thing that you use in logistic regression. You can even have a linear activation function. Sometimes a stepwise one is preferred, which is actually what we'll use here. So let's have the activation function be passing the value out if x is greater than equal to 0. Otherwise, we return 0 as the output of this node. And you can see, if I scroll back up to the example, that would work out pretty well, right? As an activation function, because anytime I'm at some sort of value for the output of this linear model that is less than this, I just want to output 0. But otherwise, I'm going to output the results of some sort of linear combination of my points, which again, if I just have one variable, it's going to be a simple line with one parameter to it, with one input parameter to it, size, right? So that is what one node of the neural network is. It's really just a linear combination of something and then an activation function that kind of just like deforms it in some sort of way. Not too complicated. This concept also works for classification problems as well. Maybe we're not predicting a real value number, but we're predicting whether something is of one class or another. So I drew up another made up example of a bunch of students, whether they not pass or failed. I was more optimistic about that, whether they got more than a B plus or less than a B plus. And I collected data about how many lectures they attended and maybe what their midterms grades were, right? Now you can see the very obvious decision boundary I should have. So for this, we'll do exactly the same thing. We'll have those 2 parameters going into a node. I'll name them x1 or x2 for now, but know that that's the midterm grade and attendance in class. They'll go into one node, and then output will be a 0 or 1, right? A binary value that represents whether they were greater than or equal to a B plus. So now the only difference between what I've done before with my node and this one over here is that step 1 is exactly the same. It's x1, w1 plus x2 plus a bias factor, right? And that'll give me my y prime. That goes into step 2. And the only difference for step 2 is that since I'm doing a classification problem, it may make more sense for me to use the logistic function at this point, right? I think it's usually referred to as sigma. And that'll be the output. And you'll see that all I've really done is just remodel what logistic regression looks like into the form of this diagram over here, right? This node-based diagram. And that's exactly what neural networks are. Each one of these nodes is in this context is probably similar to the first example I've shown over here, where it's a two-step process where you do a linear combination of things and then apply some sort of function to it. And there's popular functions to use as activation functions, but that's beyond the scope of what I want to talk about for now. Any questions? Okay. So where neural networks really shine is when they are able to model complex situations like seemingly with ease. The ease comes from how simple they are to code, right? And you'll see that in a couple of minutes when I get to some of the examples, how like it's almost like comically offensive how easy it is to code up a neural network, and how well it can perform as a result. But one of the ways that it's able to model more complex things is by stacking things together, right? Stacking these nodes together. So before we were just looking at a bunch of inputs going into one node and then producing an output. Why don't I have two nodes in my middle layer instead? So let's just track what one of these variables would look like. It doesn't look like yellow shows up that well. Yep. Again, G from my activation function, and just a linear combination of everything that's going on. W0 plus W1 X1 plus W2 X2. Really not any more complicated than that. And then the output of this, let's call A3. A3 is the same thing as Y. A3 would just be another activation function. These don't necessarily need to be different. So I'll give, these don't necessarily need to be the same. So I'll give them different subscripts, G1 and G3. This will be G3 over a linear combination of its inputs. Right. So overall, what we've produced here is like assembling all these really simple concepts in like basic linear algebra to produce this really clever nonlinear model, right? And it's nonlinear, especially because of these G's, these activation functions. And what I've been able to do is build a model that's a little bit more complicated with like very low cost in terms of like performance and training, because it's still just linear combinations at the end. And I've made it highly unlinear in the way that it's able to model things. So the ability for neural networks to model complex patterns comes from stacking nodes. Oops. Both vertically along the same layer, or maybe even producing multiple layers, right? Such as the diagram that you see here. And the second one is activation functions. Activation functions are critical for a neural network to perform properly, because imagine if I had just linear activation functions here. What I mean by that is maybe my G of X is just outputted X. Essentially, my multi-node, multi-layer structure over here can just be boiled down to one linear combination, right? So now, instead of having a complex nonlinear model for something, if all of my activation functions are essentially linear, what I've done is just made a linear model of all of the inputs. And that is not very strong in terms of model complexity. So activation functions are a big driving factor in the success for neural networks to be able to model complex things. All right, so here's just a summary of what we talked about. What I want to get into next is a little bit more of a layman's term topic, talking about like intuition behind what a neural network, what we're hoping a neural network is able to do, like what the motivation is behind this multi-node structure. So I have another example here where I'm trying to, this is a little bit depressing now that I think about it, the likelihood of hospital admittance within a year. And I have a couple of parameters for a bunch of people and historical data on all of this, right? Those parameters include the age of an individual, the number of prescription drugs they are currently taking, what their profession is, and maybe something about where they live, their residence. And what I'm going to do is manually perform a little bit of feature engineering. Let's assume that I did a bunch of domain research on this. And I know that if I combine the parameters of age and the number of prescription drugs they have in some sort of way, I'll be able to glean whether this person has a chronic illness. Right. And the reason I'm combining these is because I believe that knowing whether they have a chronic illness or not is a better predictor of determining whether they will be admitted into a hospital. Let me start that over. The reason I'm combining these two features together into a third meta feature, chronic illness, is because I believe that chronic illness will do a better job at predicting the likelihood of hospital admittance as compared to these raw features themselves. If I know the age of a person, that's much less powerful in terms of like predictive power, not statistical power. It's much less useful as a predictor for this output than this new one that I've generated. Let's do another example. Let's say I can combine a person's profession and their residence to get some sort of like index for toxin exposure, right? Where they typically, what kind of work do they perform? Do they have to work with, is it a labor job, stuff like that, right? Combined with where they live, right? What's their water quality like and all of that, that can give me some sort of measure of how many toxic things that they're exposed to. And again, the same concept applies where I believe that this new thing that I've come up with, this new variable, will do better than these guys in terms of predicting the Y variable that I want. Right, and I don't even need to necessarily combine more than one node. I can just take maybe just profession here, mold that variable in some sort of way to have it reflect the chance that a individual will be in an accident soon, right? Maybe they have a labor job instead of a desk job. And then what I'll do is I'll simply just combine all of these guys. What I've essentially made is another neural network diagram, but I've given it like a bunch of human concepts to motivate its multi-layer structure. And this is a good like rationale for wanting to use a multi-node structure. You can think of each one of the intermediate nodes within a neural network as like combining features together, features being the input parameters or factors, into new factors or new features that perform better against your performance metric than the raw features themselves. And in deep learning, that is called, oh, I'm sorry. Feature engineering, right? I mentioned the term feature engineering before, and it's because you don't necessarily need neural networks to be able to do it for you. Going back to the original concept of trying to disambiguate agent-based AI from machine learning, remember that we applied the semantic properties to our agent-based AI so that we were kind of like telling it how to do feature engineering on its own, right? We were doing the feature engineering by building the epistemology up front and then telling the agent like exactly coding what that is. Remember when I said how machine learning differs from this is that it assumes a model from data. Another benefit of that, especially for deep learning models, is that feature engineering is performed by the model itself. Right. And everything that I'm scribbling on these whiteboards and my awful handwriting is also reflected in the slides, so worry not. All right. So even though we've very colorfully described like a good way to maybe model this problem and go about using a neural network, like a motivating reason to use this neural network structure on this problem, I've lied to you. This isn't really how neural networks work, right? We would want some a neural network structure that had like these human interpretable concepts as its meta features in its intermediate stages to predict the likelihood of admittance, right? That would be a very good, well interpretable model. But neural networks don't do that, right? And they don't do that on purpose, by design. What really happens when we build one of these models is that you'll define all of the input parameters that go in, and then maybe we've built motivation around a 3-node 1-layer structure. So let's build a 3-node 1-layer structure, except instead of selectively choosing which nodes go into each one, there's what we'll do is connect every node from the layer before it to the layer after it. This is called a dense layer, and we'll have the training kind of choose what these nodes will represent. And after training on a large data set, we will, if the model performance is good and everything, we'll have a model that does do a good job of predicting the likelihood of admittance. But what we can't guarantee so easily is that chronic illness, chance of accident, or exposure to toxins are reflected in any one of these nodes. What we can guarantee, as long as performance is good, is that this model does a good job, right? It learned, going back to my slide about learning, but what did it learn? It learned how to predict likelihood of admittance. Okay, well, what is it like intermediately calculating to do that? I don't know. And it's very, very difficult to know. This is a current area of research, very interesting area of research, but overall it leads to this this trade-off, the neural network trade-off. They're very hard to interpret, but very effective at feature engineering, which is why you would use it. Going back to the example of cats in an image, right? That's a very good example of building a model that would be hard to interpret, but very effective at feature engineering. And the feature engineering in that cat example is especially hard because of all of those rule-based reason things that I mentioned before. I don't necessarily need to care about how an eye or how a cat is represented in an image, right? I don't care about the feature engineering part, just do it for me. That would be a good like case of using neural networks. Okie dokie. So here's another example. If you guys have done like any kind of neural network tutorial or read any book about it, you're probably familiar with this data set. It's called the MNIST data set. I have a Wikipedia link on the bottom. It's basically just a data set of handwritten numbers, right? They're all images, 28 by 28 pixel images. And each one of them is one of the numbers 0 through 9, 10 numbers, right? So a good like training example, a good case study for this is, given any one of these images, what number is it? And this is a very popular thing to use for neural networks. What you'll do is you'll take this entire image and you'll see that each one is broken down into its individual pixel values. This is grayscale, so there's only one number per grid point. What we'll do is we'll flatten out the image, right? Right, so here's my image of a 6. What I'll do is I'll take the first layer and plop it vertically. And then I'll take the next layer and plop it underneath. This process is called flattening until it's a one-dimensional array. Basically, we're just squishing one of the dimensions out entirely. And in that way, we've arrived at basically a neural network structure where the output is, instead of just one thing, we'll have 10 things, where each one is, what is this thing a 0? Is this thing a 1? Is this thing a 2? All the way up to, is this thing a digit 9? Right? And we can make it multi-node. We can make it a multi-node structure as well. I'm missing the number 0 here. Anyway, that concept of meta feature engineering can apply here too, and we can also apply like a pretty good like human concepts to why this would be true. Let's think about what we can hope for these hidden layers to kind of model, and if in terms of like aspects of the image that'll help us predict whether this is an 8 or not. So examples of that would be, maybe the first layer would be detecting straight edges or round edges or something, detecting black space or space where there are like actual strokes and lines. That's what early layers of the neural network might be able to discover. Moving forward into the structure, we will be able to glean more complicated meta features, right? And those more complicated meta features could include complete loops or arches, right? Semicircles within the image. And that metaphor from before about, or that the meta feature engineering concept from before really stands out over here, right? Because instead of knowing just whether one of these pixels was black or white, knowing whether there's a straight line in it is much more important to be able to determine what number exists in this image than like just knowing the raw pixel values themselves. Are there any questions?
There was a question about your W subscripts in the example that you drew up, but I think you had the same weight subscript or like weight value going into 2 different nodes.
Oh, okay. I see you answered it. Thanks.
Yep.
So yeah, this is another reason to motivate this multi-layer structure for an image example. But again, just like before. Oh wait, no, I'm sorry, I skipped a step. This is it pictorially represented by this wonderful YouTuber, 3 brown, 1 blue, or maybe it's 3 blue, 1 brown, I forget. But he has a very good video where he animates how neural networks kind of work. And in this animation, hopefully it's coming through well, you'll see the feature engineering that we hope that this neural network would be able to perform to ultimately determine what digit is contained in this image. But ultimately, just like I said before, we can't be sure whether straight edges or round edges and stuff are discovered in this layer, and we especially can't be sure that straight lines, round lines, or loops are discovered within this layer. That's kind of up in the air. We can, if we like very much wanted to guide the training of this neural network model, I'm sure we can do it. But if we had no limits on how this neural network is to be trained, which is more optimal, right? Because as long as you define your performance metrics properly, that is what you would want it to do. Why would you restrict how it performs feature engineering? If you do let it like take caution to the wind and learn on its own, it's very likely that these layers near the end of the neural network, closer to the prediction side, will reflect parameters that will reflect features that are not human interpretable. And again, just goes back to the black box concept. Okay. So these last two slides that I'm going to go over are really just summaries of neural network advantages and disadvantages, because hopefully up till now you've gleaned like a better understanding of what this node structure looks like and what is actually in it. It's just math. One of the biggest benefits that we've talked about was feature engineering, right? It performs this whole process of understanding the data and maybe manipulating the data in some sort of way to make progress on performance on its own, right? You don't need to perform domain knowledge, domain research necessarily, right? In order to get a good performing model. So whether that's a good practice or not is up to you, but that is one of the benefits of neural network modeling. In the case of maybe an example where you do want good model interpretability or good domain influenced modeling, neural networks might not be the model that you choose, and you might stick with something more traditional like regression or maybe decision trees. But in the case of just figuring out if something's in an image, right? Going back to the example we set over here, why do I care what's happening in the middle as long as it predicts cat properly? Neural networks are also very good at learning complex patterns. We talked about that before. That entirely comes from the use of activation functions and stacking multiple nodes together within one layer and within several layers horizontally. And there's a lot of theory that goes behind that I'm kind of glossing over. So maybe a future deep dive and on the internet will get you those answers. For complex problems, accuracy almost always increases as your data size grows. This is especially useful for us now because we have large data sets of like almost anything that you can imagine. Transfer learning is something that I haven't talked about, but it's good. It's a good thing to mention. Basically, if a neural network was trained on a problem that is similar to a problem that you wanted to solve, for example, this model that we've built here for detecting if a specific digit is contained in an image, maybe I want to build a similar model, except not using digits. I want to detect alphanumeric characters or just alphabetic characters, right? Of the same thing, 28 by 28 pixels. So another benefit of neural network modeling is what I can do is chop off the entire first half of this neural network model and just change the prediction layer and then use that as a starting basis for my training. And it turns out through practice, this is extremely useful and like very successful. So that's a very simple example, but you can hopefully glean how it can be useful for other examples too, particularly in the case for specific types of models that are trained maybe using Google's data sets that Google or Facebook do for us, right? And they open source models for us. We can leverage essentially their computing and their large data sets by just adopting or downloading like their checkpoint model and then moving forward with training based off of that. All right, some of the disadvantages now. For more complex problems, obviously we need more a deeper structure with more nodes and stuff, and that's when things start to become more computationally expensive, especially because we need the style of neural networks necessitate large data sets, right? Linear regression can get by with a traditionally small data set, but even the more basic neural network models require pretty large data sets to work. So just a natural byproduct of that is that they perform better when you have custom hardware attached to them. And I'm sure you guys have heard about specific GPU clusters that are dedicated to training neural network models. It's a black box algorithm that we've discussed that to length. And this is an interesting one that I like to mention. Crafting an architecture to suit a problem is very difficult. This gets to the whole idea of building a neural network is easy, but how do I know which hyperparameters to choose for my neural network? And there are so many. How many nodes per layer? What activation function should I use for each one? How many layers should I use? What type of layer should I use, right? We only talked about one type of layer, but there's a lot of freedom in how these things can be modeled. And overall, it's very heuristic, right? I shouldn't say it lacks rules or best practices. Instead, I might change that to lacks like rigid design, like a rigid design flow, because it's still more of an art form. Typically, when I do a project for deep learning, what I'll do is I'll try to leverage the transfer learning concept I used before, see if somebody has solved a problem similar to me, and then use their model as a template for moving forward. Another thing I'll do is just look at things that more successful like research labs have put out as starting architectures for case studies that are good for maybe image processing, voice recognition, or something like that. They might have a template architecture to start off with that they've like explained and reasoned about, and I'll use that as like a motivation to start. But overall, designing it from ground up on your own is very, very difficult. And again, I mentioned this one, dependent on having massive amounts of data to train on.
Hey, Roshan, there's a question that popped up,
Sure.
which is perimeter optimization sounds like a really good application for DOE. Do you know of anyone that does that?
No, not a person. Did Doug ask that?
No, Jason Martin.
Oh, wow. I see what you're doing, Jason. It is a good application of DOE. Hyperparameter search it's an entire topic on its own that I'm sure anybody over here in this conference can talk about to length. And it's very, very big problem, a very, very big interest area for neural networks, especially, right? Because like I said, there's so many hyperparameters to choose from, and DOE would be an interesting one, especially because DOE works so well with optimizing a search space to like a restricted set that you're interested in, and then being able to like explore it like in a really optimal fashion, like assessing each one of the factors that goes into it properly before deciding where to explore next. And yeah, Douglas Ray is my go-to expert for DOEs. Any more questions?
That seems to be the only one right now.
It sounds good. So I'm surprisingly very much on schedule, and I planned on taking a break, but I might skip it. Everybody is okay with it. I'll assume we are.
Yep, go ahead.
All right, so now we're going to the last module, which is more of the hands-on stuff. So I'll move my tablet aside over here. Hopefully you guys can see my desktop and everything that I'm doing. If you, Rebecca mentioned this earlier, if you go to my talk, little panel thing I have over here, there's a link to all of the session materials. It's hosted on GitHub, so you can just download a zip for all of that. There isn't enough time for like a realistic back and forth with you guys testing things out and then me explaining it, or like you walking through it with me. What I'm going to do instead is just walk through these notebooks on my own at like a relatively brisk pace, and then hopefully you guys can go back through these and work on them on your own. So when you download the zip file, you'll have a folder structure that kind of looks like this. I want to draw your attention to this one Word document in here that walks through some of the prerequisites that you'll need, which is just installing a Python environment. I'm recommending Anaconda as a Python environment, which I'll talk about a little bit more in a second. Talking about what Jupyter notebooks are, which I'll kind of just jump into, and then discussing TensorFlow. So if you guys want to actually run through the notebooks that I'm doing here, please read through that Word document first. Okay. So the first thing I mentioned is this program called Anaconda. Anaconda itself is kind of just a distribution for Python. Python is an open source language for doing basically anything, right? It's a high level interpreted language that you can perform anything on. And one of the troubles of new people going into Python is that you have to manage a lot of the low level computer sciencey stuff on your own. And there's not always good utilities for that. What I mean by that is, just like with R, there's individual packages for specific libraries, since it's open source, that you might want to ingest and then make use of. For example, Tensorflow, or maybe a numeric optimization library or something like that. And each one of these are controlled and moderated by different groups, and they release on their own schedules and stuff. They try to communicate with each other, these groups, to make sure that things align, but occasionally you'll have the case that an update in one package will break all the stuff for the other packages. And this is one of the prime examples for why Anaconda is so good for new people coming into data science with Python. What they do is manage their own kind of environment structure. Each environment structure can be considered like a separate installation of a set of packages. And I actually included the environment, the specific environment that we're going to use for this tutorial, DataWorks 2021. And you'll see that it's just a very long list of a bunch of characters, and you'll see that the version numbers are defined for each one. So what I've done is construct an environment that is useful for this training that specifically has TensorFlow here somewhere, right? TensorFlow 2.3, a couple of other libraries like Pandas and NumPy of specific versions. And what you'll be able to do with this YAML file is directly mimic my environment using Anaconda to just download it. And then I'm working with a command line interface here to be able to work through it. But there's another option called Anaconda Navigator that might be more, it's a GUI-based approach to navigating the same kind of thing. This console is a little bit more responsive, so I'm going to stick with that. Just going to navigate to the folder where the tutorial stuff is. And the first step I'm going to do is, once I'm in this Anaconda prompt where all my environment variables are set, I'm going to activate the environment that I've made. And you'll know that it's activated because the space environment changes to DataWorks 2021. Now, all of a sudden, I'm in the installation instance that has TensorFlow, Pandas, and all of those other things configured for me. And again, and the Anaconda distribution is very easy to use because they compile like that dependency map for you and like make it pretty easy breezy to just kind of get up and running and started. If you get into more like experimental stuff with Python programming, you'll occasionally want to like construct your own environments manually and not rely on the dependency trees that Anaconda has, but that's another story. So what we're going to do is use Python, right? So from this console, I can just run Python on its own, right? X equals 3. I can print out what X is. I can print out strings, just basic Python stuff. I can also maybe I'm going to save this to a file. Right, so what I've done is have X equals 3. Actually, let me show you the file. I've created a file called test that just has this code in it, X equals 3, print X, and I named it test.py. I'm in that directory now, so what I can do is just call the Python program by writing Python and then execute that all the script in that file, and then I get it. This is Python in like the most simple form, right? So I've already shown you 2 applications that Anaconda has given me that I've used, IPython, which is interactive console for Python, and then just Python, the application on its own, which is execute the interpretable thing to run a Python script. Another thing that, another very useful tool, especially among data scientists and machine learning, that whole statistical community, is this thing called a Jupyter Notebook. And it's way easier if I just show you up front. So Jupyter Notebook looks like a web page. It looks like a formalized web page, like a notebook. And you'll see that I'll be able to do the same things that I did before. So I could say X equals 3, print X. It's essentially the same thing as that interactive environment that I started out with up here, right? Except now it's in a nice web GUI format with like a JavaScript layer sitting on top. And it's actually a little bit more than that, because you'll see that a bunch of obscure text showing up here. This is a web server being spun up. And then now my web browser becomes a client that attaches that web server. And the server serves up a Python environment for me, which essentially is like a running interpreter that listens to what I put in these text boxes and executes that code for me in line. So it's very useful, very neat. Overall, good for like I don't want to say experimental programming, ad hoc testing things.
Hey, Roshan, would you mind zooming in just like a touch?
Yeah.
Thanks.
How's that?
Perfect.
Okay. So I have two notebooks shown over here. Hopefully we'll have time to get through both. If anything, I'll just breeze through the last one really quick. This first one is an example for stroke prediction. It's a classification problem. And the data was given to you. If you look in the folder, I have dataset 0, dataset 1. We're looking at dataset 0. It's just a CSV file. Let's look at it in Excel. Not very exciting. Essentially what it is a bunch of metrics about patients and whether they've had a stroke or not. Man, I picked a lot of upsetting examples, you notice. So what I'm going to do is walk through some basic, like what a workflow would look like leading up to and then building a neural network model using TensorFlow. So in the beginning, if you guys are familiar with using jump or maybe R, you might be familiar with the data frame concept, right? And that is exactly the same in Python. There's a package called pandas that helps manage data frames for you. And essentially what I've done is just read in the CSV file, and now I have a object in Python that manages, that helps me manage this two-dimensional data. It doesn't also always need to be two-dimensional, but just so happens that my data is two-dimensional here. There's also useful functions built in for descriptive statistics, assessing like data types of all of my things. So I can tell which things are integers, which fields are integers, which fields are complex objects. Right? So ever married is a complex object, which probably means it's a string, and so on. I can also discover whether there's missing data, right? I see 5110 as a count for most of my other fields, but I might be missing one here. And what else? Oh yeah, I can also perform a quick ad hoc exploration of my data. And this comes with just experience with being familiar with the language. Like just the more you use Excel, the better you get at understanding what the functions and stuff available for you are. So here's a good one just to see that my predictive variable that I want to see stroke actually has like a very imbalanced relationship, right? There's a lot more points that of people who didn't have stroke versus people who did have stroke. So we'll have to address that. So initial observations of all of this is that basic data cleaning is required, right? Because I clearly have missing values, and then I'll have to address this data imbalance on my class variable somehow. So I'm not gonna like type through all of this with time in mind. So I'll just run through it. The first step I do is get rid of my more categorical variables and replace them with binary, like one-hot encoded variables, right? So I've gotten rid of the gender, male, female, other, and replaced it with just gender, male, gender, female. It's a 3-class thing, but I only need two variables to really define it completely, right? And that's the case with all of the categorical variables. Ever married, yes, will generate maybe two one-hot encoded variables, but I only need one to define the feature. So that's the first thing I did. I've decided to impute data by just using basic mean over the missing variable. And I did a little bit of outlier stuff. So this is definitely bad practice because I'm handling outlier data in medical records, specifically for what is this? This says average glucose level. I probably don't want to trim outliers for stuff that in this field, but the purposes of this example, I've decided to trim it just to make things work out a little bit more. So I have a little script to do that. And to address like the sampling issue that I have with the much larger negative class, I'm going to employ a oversampling technique called SMOTE. So you can get more information on that here. So essentially what I'm doing is SMOTE in short basically just generates new samples of the underrepresented variable by making up new points for it that are realistic according to the point space that I have. All right. Finally, we can get to the model building. Up until now, all I've done is just massage my data, do a little bit of data pre-processing to get to the point where I have these two variables, X train, which is all of my points kind of like put together into this dimension shape. I have 16 individual input parameters and this many points, this many individual instances of points. So I have an X train, a Y train, which is the binary variable stroke that's associated with each one of the X trains. And then I also have X test and Y test, which I'll use for validation purposes. So that's all the upfront work that I've decided to give to you. Now what we're going to do is build a TensorFlow model. I have a slide that kind of helps walk through this. There we go. Actually, let me start from the beginning because I think it's important to, I was going to skip this, but I think not. So TensorFlow is a Google Brain project. It's an open source platform for building computation graphs, essentially. And it's widely used for machine learning and training because these computation graphs are optimized for collecting gradients over this computation and performing like linear algebra operations over like a lot of like batched operations. So there are interfaces for a bunch of different languages. I think R has one now. Python and Java definitely have one. There's a JavaScript interface. We're obviously using the Python one. What's important to note is that TensorFlow itself, its actual computations are written in low-level C. They exist as C binaries when you download TensorFlow. And Python, all these high-level languages, the interface for it is actually just an interface for you to be able to write code in a manner that's comfortable for you so that TensorFlow can massage it into its C binaries functions. Right, so at the S it's C++, but we're looking at the Python interface for it. And when I said computation graph earlier, this is what I meant. I have variables that are going into these nodes that represent operations, right? And essentially TensorFlow just builds large versions of these that represent the neural network operations. And then when I'm ready for training or actually processing over something, I'll just feed each one of these variables in a tensor, which is an n-dimensional array, right? To be able to perform an operation. And TensorFlow is just very much optimized to perform this kind of math for you. And it has utilities for distributed computing and parallel processing and all that kind of stuff. So it makes it nice. All right. In terms of building a very, very simplistic neural network model, it really just boils down to these three steps. As you get more complicated with the model architectures or the training processes, how you want to run the training, maybe you have like a batched approach to it, you might need to adjust these steps accordingly. But in terms of building a very basic neural network model, like 98% of all the models I've made can boil it down to one of these things. And it handles complex architectures too, between convolutional neural networks, residual neural networks, really don't stray too far away from this. Occasionally, if you guys have heard of like general adversarial networks or maybe autoencoders, you might need to adjust one or two of these steps. So we're going to basically just mimic these steps over here. It's that simple. And then hopefully you guys will be just as offended as I am at how simple this is. Look how ridiculously easy it is to build a neural network model. So the first step is to define the model architecture. So we'll call it model. We're going to import, we're going to import TensorFlow and a couple of utilities for building dense layers, which we talked about before, right? A dense layer is just a layer of nodes that have all of the inputs connecting to it. And then I'm going to apply a regularizer to it as well. You'll see that I can actually adjust each layer's individual nodes to have a different regularizer if I wanted. So what I'm going to do is import a sequential model. What a sequential model means is that my data is flowing in essentially one direction, which is the majority of most neural network models. And what I can basically do here is just linearly in an array build out my neural network. So I want 3 dense layers, and maybe the first layer I want 10 nodes. The second layer, let's go up to 20 nodes. And in the final layer, that'll be my prediction layer. I want 1 to predict the stroke category, right? Remember that each node has a linear combination of things and then also an activation function. So I think it's just activation. let's use a ReLU activation for this. This can also easily be linear if I wanted it to. ReLU is a popular choice. Stands for rectified linear unit. It just looks like this. Remember, I had a stepwise linear function. I also said sigmoids can be used. This is another type that's been experimentally shown to be very useful. All right, and then let's add the regularizer here. Out of the screen. Let's see if it gives me an error. All right. So I've defined the activation function to be used for all 10 of the nodes in the first layer. I'm actually going to, I want the same thing repeated for the next layer. And for the output layer, since it's a prediction class, since it's a classification problem, my activation should be something that's akin to that. I'm going to make it a sigmoid activation, which is the same thing as the logic function or the logistic function. All right. The next step of model building, we'll go back to the slides over here, is compiling your model. What you do in the compilation step is define like meta properties about your model, not just the structure of it, but not the structure of it, but maybe what optimizer do you use, what loss function or error function you want to do, what metrics do you want to track. So let's do exactly that. Model.compile. Very, very simple interface. So the optimizer, let's use stochastic gradient descent, the one that we talked about earlier. What's the next thing? The loss. Since we're dealing with a binary classification problem and we're outputting the output of the logistic function directly, we want the loss function to be a binary cross entropy. And in terms of metrics, since it's a classification problem, let's track accuracy. And at the end, let's just print a model summary to see where we're at. I made a mistake. Sorry, let me know if you see my error before me. Install optimizer. It's definitely being made. Oh, well, for some reason, I think it's, maybe I'm stuck in non-executable.
Hey, Roshan, you do have a comma after sigmoid. I don't think that would change anything though.
No, I don't think so either.
Can you can't plot the neural network diagram, right? I think that's another TensorFlow command.
That's what I'm trying to do. So what's weird is that it is a valid model. Like I just ran the training for it. It just won't let me print the model summary. Weird, huh? I think I might be stuck in non-eager execution or something, which is beyond what I wanted to talk about. Yeah, it totally worked. Anyway, so where I got caught up was I was trying to print out a summary of my model that described all of the nodes and what activation functions there are, how many parameters it introduces at each layer. Let's see if it works now. Yeah, that was annoying. So it seems like it only worked after I initialized my model for training. So there is a TensorFlow is a little bit quirky in that this computation graph sometimes needs to be complete before you can understand you can ask TensorFlow about how the model behaves and stuff. So that's the issue I was having just a second ago. So when I executed model training, TensorFlow knew to like combine together everything, and then I can ask it properties on my model. So the property I asked it was summarize your layers for me. So I can see that I have 3 dense layers here, the shapes, the shapes of my parameters that are traveling through them, and how many parameters it introduces. Going back to my 3-step process over here. The last thing I'm going to do is run an iteration of training, and the function for that is called fit. And all the input parameters are as you would expect. The first one being my data set, right? X train and Y train, right? So the data set that it's training on, I decided to employ a validation split on the training data set so I can get a sense of how the training is running throughout this process, and the number of epochs I want, how many times it iterates over the data set. So I ran that a second ago, and you'll see that I get pretty good feedback. When you have a particularly long training, it's good to see like this progress bar, but it's hard to interpret these numbers correctly. So I decided to plot them. You'll see that the training and validation numbers for accuracy and the loss metric are plotted here. And you'll see I have relatively good behavior. And I'm going to additionally import some other useful metric tools for making a confusion matrix and calculating effluent score on like the test set that I've decided to set apart. And you'll see that my model is kind of bad, right? So I have really good feedback for the negative class, but my type 1 and type 2 errors are a little bit need to be worked on. So there's a lot of opportunity to move forward here, but you can see that actually building the neural network model took like almost no time. And there's just a lot of flexibility, even just within the built-in parameters for this dense object that's given to me. I can choose to easily add more layers and experiment to see if that works out better. I can go scroll back up and maybe perform more manual feature engineering. Maybe I want this to perform more feature engineering for myself. Maybe I need to adjust the kernel regularizer. All of these are like valid steps for moving forward. But like overall, this notebook can take you like maybe 5 minutes to put together, and already you have a deep learning model that like doesn't perform that well, but it's a good starting, like a good basis for moving forward.
Hey, Roshan, we have a couple questions.
Sure.
The first one is if you can actually plot the neural network diagram, which I feel like I've looked into, and I think you need something called TensorBoard or something if you want to actually see how the model looks, I guess I'll say.
Right. Yeah, good question. So that's not something that was planning on covering, but TensorFlow on its own has so many utilities and stuff. All I did was just basically show you the bare bones structure for building a neural network. But there's also, since everything is written in JavaScript now, and essentially my model exists within this Python environment, I can interact with that model in any way that I want and use JavaScript's like rich library to be able to plot things. So one of the more popular open source projects for being able to plot all this is called TensorBoard. And I feel like this animation over here just kind of speaks for itself with the kind of stuff that you can do. You can easily view your training data. This is a model, what I think that question was about. Kind of went by too quick, but you see the computation graph over here of exactly what your neural network is going through for debugging purposes and stuff.
We had another question that asked if you sent a solution to the Kaggle competition.
No, I didn't. No solution yet. Any more questions?
That's all for now.
All right. So in the last couple of minutes, I'm going to try to breeze through the second notebook that I had planned. It's an image classification problem, and I promised my dog that he would show up here. So here he is. This classification problem is a binary image classification problem with this data set. Let me show you. Under the dataset 1 folder, I have 2 folders, test and train. And the reason I'm doing this is just to show you how easy it is. Like I grabbed these photos off of my phone because my phone consists of just funny pictures of animals, basically. So this is a bunch of pictures of my dog in one class. His name is Ugly, and his best friend Darwin. Right, all these pictures I just had on my phone, and I decided to upload them into this folder structure. So I have defined a training set with 2 classes, and I defined a test set, again with 2 classes. And these are just set aside to determine whether my model performs well or not later, right? Just a couple of images of both dogs. Again, I just want to show you how ridiculously easy it is to just make a quick convolutional neural network model, which is what we're about to do. Maybe...
Hey, Roshan, one quick question that maybe you can kind of answer as you go through this.
Okay.
But are there any best practices for like what order you would change things to improve the accuracy of your model? In particular, different hyperparameters like the number of layers, number of nodes, things like that.
Yeah. So off the top of the bat, I like purposely made this a little bit too complicated. So I think that I think that I would start by reducing the complexity of this model here. But even maybe before that, do a lot more domain research. There was definitely something wrong with the way that I just decided to toss out all of those outlier points instead of just throwing away data, which is the worst thing you can do in a case like this. Maybe try to understand it more. Maybe I need more manual feature engineering to be able to make sense of that. I think overall the answer to my question is not on the neural network side. It's more on like the data parsing, understanding your data, domain research. That's where I would move next for sure. But after I maybe am more comfortable with that, then I would experiment with just like reaching out in like different points of hyperparameter space to try to test out different types of models. So this I would consider like a relatively deep model for this application here, because I have 2 nodes of 10 and 20 when I only have like 15 input features. I might try one that's much more simple, maybe just one hidden layer, and then one that's a little bit more complicated, and just see how both of those perform. Eventually, when I'm more comfortable with the problem, and if I have enough time to do it, I would build this thing over here, construct a model pipeline that searches the space of neural network architectures, searches the hyperparameter space for more optimal configuration. So that's more of a systematic way to do hyperparameter tuning. Going back to that question about DOEs, that would be an appropriate use for DOE. Bayesian optimization is a good example too, but that would be like late stage. I hope that answers the question.
I think so. Yep.
Okay. So just jumping through this notebook, essentially what I've done is take images of my phone of these 2 dogs, pre-process all the images so that they adhere to strict requirements for dimensions and stuff. Because remember, all neural networks basically have to have, when I train them, the input size is fixed. So what I decided to do is change all of these to a size of 50 by 50 by 3. So I retain the color dimension of RGB, but each image is now a 50 pixel by 50 pixel image. And then in addition, since I only have 65 images in my training data set together, that's not nearly enough. I've employed this process called image augmentation to kind of mimic that I have more data. So if you'll see, if you look through, you'll see that essentially what I've done is apply random perturbations and deviations to my data to mimic like the qualities of a larger data set. Some of these images are flipped horizontally, some of them are zoomed in, some of them have like random noise and perturbation. All of them are realistic adjustments made to the data to kind of simulate that I have a larger data set that I'm working with. And that's a good technique for when you don't have a lot of data at your disposal. For example, I only have 65, but what I've essentially done was craft a Python object that generates like adjusted samples of my data on the fly. So I don't have to make 1,000 images of this. I've built an object that can randomly sample from a larger pool of images using my 65 as seeds. It's another very useful thing that TensorFlow lets me do. So in the beginning in this notebook, if I had more time, I would go over the linear model that I made, which is more akin to this flat structure that we were talking about over here. Flattening all the pixels into a one-dimensional set and then just having them travel through a set of dense layers, which is what I got over here. And you can see exactly how many parameters I have and stuff, right? I flatten it, apply a dense layer, and then an output layer for sigmoid, because again, this is a binary classification problem. And then through training, you'll see that it doesn't actually perform that well. This is my test set image. Output is a probability of confidence whether the image contains a picture of Darwin or not, the Shiba. And you'll see that it does do relatively well for predicting whether the dog is Darwin or not. But the confidence interval for Ugni is not so good. So we can definitely make an improvement on it. So enter another type of neural network architecture, which I have a example notebook about over here. And there's a slide. Slide 44. The difference between this neural network architecture and the other typical ones that have the basic dense layers is that instead of having all of the input parameters from one layer pass into the next one, instead we're going to mimic like a lens looking over the input dimensions, similar to what this animation is showing here. And we'll only look at regions of data at a time to try to grab spatially relevant features. And essentially what we're doing is performing feature engineering with the context in mind that spatial awareness is useful, right? Because we're in an image. So feel free to look through this notebook to learn more about this convolution operation and what a convolutional error does. It features my dog Ian. But you can see that like an example of one of these lenses can have drastic effects that emphasize spatially relevant features in this image. And so for this, you can see already that edges are detected a lot easier, which would be very hard for a dense layer to be able to pick out. So you'll see that my sequential model thing still stands even for this convolutional neural network. The only thing I've done is import a new type of layer called conv2D and a supporting layer called a pooling 2D. And really all I've done is just replace my dense layers with those with a little bit more extra parameters. Read the other notebook to understand what these parameters are, but they're really not too complex. And after training and assessing model performance, you'll see that I perform much better on the resulting data set. Actually, I don't. Oh, I know why, because I didn't train long enough. So that's another thing I wanted to get to. The original training set only went over 100 epochs, but I've like tripled the complexity of my model by including these convolutional layers, two layers of convolutional layers. And you'll see from my training that I haven't plateaued out enough. So I would need additional training on my training data set to perform better. Well, then once I do, you would see that the performance on the training data set or the test data set is loads more successful. And I can grab other pictures of Shiba Inus and then be able to detect Darwin properly. Overall, I think this is a really simple problem. So this simple solution would work out. I know that I was really interested in Dr. Erin Landis's tutorial yesterday, where she introduced the problem of determining whether an image contained a husky or a wolf. And that entire discussion was more centered about like the data integrity of a model detecting snow in an image and automatically assuming a wolf versus a husky or not. But that would be like a fun next project to try related to this.
Hey, Roshan, there's
Yeah.
only a couple minutes left, but when we're doing like the image rescaling or the data augmentation, do you kind of know like how much of an effect that has when we're like making all of the images the same size?
What do you mean by that? Can you elaborate? By effect? Oh, let me read the question. Do you know how much an effect this image scaling typically has when you enforce common size? If you're talking about like loss of detail, it's really little. Obviously, like you will want to retain as much information as possible, especially as your problems get more complex. But what I done over here was I changed them all to 50 by 50 or something like that, right? Even that's probably retaining too much. I probably could have gotten away with a 20 by 20 image, especially because Darwin and Ugni look so different to begin with. I'm probably adding unnecessary complexity by keeping the image so large. But in typical problems like with like Google's data sets, they will downscale their images down to like 150 or 250 by 250, something like that. And in terms of if you're referring to the image augmentation thing, this has nothing but good effects on your training data set because it introduces some variability to prevent overfitting, mimics a larger data set, and as long as your perturbations are more realistic, let me see if I can point out. Here we go. So these are the perturbations that I've applied. A shear range, which is how much I want to like distort the image, which kind of just mimics like me taking a picture from a different angle. A zoom range, right? Again, a realistic perturbation, and a horizontal flip. All of those are like reasonable assumptions for me to like artificially generate more images in my data set. So this can only help your training. Is there a TensorFlow package for Julia? I doubt it. Julia is a super cool language, but nobody supports it. Yeah, I think this is just a amateur, someone's amateur project that maybe you can build off of, but unfortunately, no.